Okay, so I just wanted to do a couple of remarks on 3.2. We're not going to spend a lot of time on this, but one important point comes up in section 3.2, and that is the difference between variables and parameters. Okay, so if we have a function like this, right, we think of our x as our independent variable, but then we think of a, h, and k as parameter values, and those are values that we can change in the model, but they stay fixed when we actually work with the model. So we assume when we write this model that a, h, and k are somehow fixed, and then the x is changing. So you can kind of think of them as like little control parameters, right? Because in this example, do you recognize the form? This is a parabola, and the parabola is centered at the coordinate hk. And so you can think of the hk as controlling the location of the vertex. And then what does the a do? If the a is positive, the parabola will open up, and if the a is negative, the parabola will open down. Okay, so you can think of hk as being control parameters for the location of the vertex of the parabola, and then a is controlling whether the parabola opens up or down. But in all cases, right, no matter what the a, h, and k are, as long as a is not 0, then this is a parabola. Good. And so we can work with these parameters then, when we differentiate, because, the derivative is just going to treat those parameters as constants. And so when we take the derivative of this, for example, we'll get a 2a times x minus h, and then the derivative of k will just be 0. Yeah, and so you could actually see where the location of the vertex is, right? By if you set the derivative equal to 0 and solve for x, then x is equal to h here, right? And then if we put h back into our function, we get the value of k for our y-coordinate of the vertex. Good. And so you can see that the derivative, the a value, also controls if the derivative will be positive or negative, along with the h, right? Because so if you were to do a sign chart on this, what would it look like? 2a times x minus h, right? So at x equals h. So if x is smaller than h, right, then this is going to be negative, and so our derivative is going to depend on whether a is positive or negative. And so if a is positive, then we would have a negative number here and a positive number here. But so this is for a positive. But if a was a negative number, right, you would switch those, right, because then you'd have negative times negative, positive, and then if a is negative, you'd have negative times positive is negative. Yeah, so the a can switch the signs in the derivative. Okay, so that's what the section 3.2 is about. We're looking at to see what happens with various parameters in a family of, we would call this a family of functions, right? Because depending on what you choose for a, h, and k will give you a different curve. But they're all parabolas, right? And so similarly, the last problem in that section is kind of interesting. It's a statistics problem, actually, and that is that it takes a look at the function e to the minus x minus m squared divided by 2, I can't read it, 2s squared. There we go. Okay, and so it asks, what is the role of m and s in this function? And so that's used quite a bit in statistics, because as it turns out, the shape of this curve is a bell-shaped curve that's used in statistics. Actually, I should draw it a little bit differently. The center of the hump here is at x is equal to m, and then the s controls the width of the hump, if you will. Yeah. So by changing these parameters, right, you can change the look of your exponential function here, this bell-shaped curve. And so this is why it's used quite a bit in statistics. This curve is used quite frequently. Okay, so I think we're just going to leave it at that, and then we're going to go on to optimization in section 3.3.